And that is on page 71, 71. Okay, when we consider the nature of the reactants, we are comparing different reactions with different reactants and different products. In contrast, okay. So this is just like what we were saying when we were doing this for factors affecting rate. This is for, it makes the difference between two different reactions. It makes the potential energy of the reactants different as well, and the products. Potential energy of the reactants, potential energy of the products, and the activation energy. So basically it changes everything about the graph, because it's a different reaction. Shocking. So here is reaction A, reaction B. Look, they're different because they're for different things. Shocking. Okay. What effect do other factors have on potential energy diagrams? So catalysts make a change to a diagram. Nature of reactants just give you different diagrams because they're different reactions. What effect do concentration, pressure, temperature, and surface area have on potential energy diagrams? They have no effect. None. Nothing. Okay, so really, the only thing that affects potential energy diagrams is catalysts, because I think nature of reactants is kind of like a stupid thing because they're different reactions, they have different graphs. So the only thing that affects potential energy diagrams is a catalyst. There is another one. And the second one is an inhibitor, which you can think of as an anti-catalyst. So basically, it just makes things hard to react with each other. So what it might do is, if I had these two pens, I'll wait until you're finished writing. If you have these two pens and they need to react and they need to collide this way so that they can switch caps, if I was an inhibitor, maybe I bind to this molecule here, right? A chemical binds here. Now, what does that do? Makes it harder. I would have to, these things would have to bash into each other with enough energy to dislodge the inhibitor, and usually inhibitors bind fairly tightly, right? And yeah, it just, so what would an inhibitor do to the activation energy? An inhibitor would make the peak higher. Okay? So catalysts make the peak higher. No, sorry, peak lower. Inhibitors make the peak higher. There's a lot of explanation here, but you don't need to be able to explain it. Okay, so I would be just as tempted to skip past this unless you feel like you would like an explanation. Anyone want an explanation? Moving right along. Okay. Why? No. Okay, here's our inhibitor. This is a graph of an inhibitor. We're now on page 75. And you can just see the graph with the inhibitor. It has a higher peak. Oh yeah, this is just labeling the axes. The x-axis can be labeled progress of reaction, reaction coordinate, or reaction proceeds. I don't know why reaction coordinate. Direction of reaction. Pick one, doesn't matter. Just recognize that's what they all mean. And I think that's it. We're done potential energy diagrams, I think. Yes. Okay, so we're done section 1.3. Moving on to 1.4. Next week, we'll have a quiz on 1.3 and 1.4 and 1.5 because 1.5 is really short. And then we'll have our test first thing the week after that. Okay?
Also, like next week.
Next week. Yeah. Because that way we can finish this. We can give you a quiz. You can get the quiz back. You can have the weekend to review, and then you can write the test. Yes?
So 1.3 and 1.4 could be in the same quiz.
1.3, 4, and 5 will all be on the same quiz. Okay. So and that's because they really relate to one another quite a bit. Okay, so we're going to now take a look at reaction mechanisms.
Where is that?
This is on page 83. Watch the video first. I don't think we need to watch the video. This was very often with AP, I have them do things independently. I'm like, go off and do this on the weekend, bye. We'll be moving on next day. Okay, so a reaction mechanism is a step-by-step process that reactant molecules undergo to produce eventual products. Any reaction that has more than 2 reactant molecules, instead of just going directly from reactants to products, what's going to happen is you're going to have step 1, where reactants go to something, and then that other something in a second step goes to your final products. Or maybe it takes 1, 2, 3 steps. But anytime you have more than 2 reactant molecules, you're going to have more than 1 step. And that's because if you imagine these particles are like floating around, they're going to collide with each other all kinds of ways, and only very rarely will they collide correctly with the correct geometry. Now let's say that there's a third particle as well, and it also needs to have exactly the correct geometry. What is the probability once we add in a third one of them all colliding? A lot lower, okay? So the probability of more than 2 molecules colliding simultaneously with sufficient energy and proper geometry is extremely small. And you should be able to explain that. Okay? Memorize this. You don't really have to memorize it. You just have to understand it and be able to explain it. But for some people, that means memorize it. So if we look at this reaction that we have here, 4 HBr plus 1 O2, that gives us 4 plus 1 equals 5 reactant molecules. So why is that reaction not going to happen in a single step? Because there's more than 2 particles, and tell your partner why, if you have more than 2 particles, it will react in more than one step. Feel free to read it if you need to, but like make this part of your memorization process. So we good? Okay. So rather than having 5 molecules collide, what we're going to do is we're going to get 2 particle collisions step by step until we eventually get the product. So what we're going to do first is we're going to have an HBr colliding with an O2, just 1 and 1. So just 1 particle and 1 particle, okay? And those 2 collide and they form a Huber, okay? Now, do you remember what happens in the arrow? In the arrow? What do we get in the arrow? That's our activated complex. So this step of the reaction will have an activated complex. Yeah, thank you so much. Okay, so even in a mechanism, we do not see activated complexes. Okay? All right. And then our Huber molecule collides with a second HBr, because remember we had 4 HBrs. So our second HBr comes in and reacts with a Huber, and we get 2 Hobers. All right? Now, each of those 2 Hobers then collides with a final HBr. So this last step is going to happen twice, okay, to use up both of the Hobers and to get us to 1, 2, 3, 4 HBrs. And we end up finally getting H2O and Br2. So we have our reactants, HBr, and there's 2 of these ones, right? So that's 4 HBrs. We have an O2. That's our reactants. So those are our reactants. And then our products, we got these guys here, and there are 2 of each because this final step happens twice. So we end up with 2 of those and 2 of those. And lo and behold, that is exactly what we should end up with here, 2 and 2. Yes? Everything else that happened in between, the Huber, what happened to it? It was produced in step 1. What happens to it in step 2? Collides with HBr, and do we have Huber anymore? No. So Huber is first produced and then it is used.
How do you know Huber is like slower than Albert? Like it says slow fast.
Oh, don't worry. We'll talk about that afterwards. Okay, so Huber is first produced and then it is used. Anything that is produced in one step and used up in a later step has a name. Let's see where I've got that name. Right there. a reaction intermediate. Okay, it is produced in one step and it is used up in a subsequent step. Now, what the heck does subsequent mean? Subsequent just means later, but you will hear the language subsequent. Okay? So subsequent just means later. So it could be made in step 1 and used in step 2. Or it could be made in step 1 and used up in step 3. Okay, it doesn't matter. It could be made in step 2 and used up in step 3, whatever. Do we have any other reaction intermediates in our reaction mechanism, which is what these steps are called? We have Haber. Yes. Okay, Haber is another reaction intermediate. So our two reaction intermediates, for example, are the Huber and the Haber. Do not get those mixed up with the activated complexes. Can you see an activated complex in the mechanism? No. I'm just going to call it an AC. Yeah. Okay, so there we are. We don't need to circle the reaction intermediates because we already did that up above. And I guess while we're at it, we could label all of our activated complexes. How many activated complexes would this reaction mechanism, this whole thing is the reaction mechanism. How many activated complexes in the above mechanism? It is as easy as you think. 3. 1, 2, 3. 1 for each step. Okay, very good. So even though our test will be the week after next, we'll be starting Unit 2 next week. Yeah, so we'll be partway through Unit 2 by the time we write our Unit 1 test. Are we good with that? What?
I would say kind of. Do we
Kind
have
of?
to write out the steps one by one?
Oh, for this? You will usually be either given the steps of a mechanism and asked to find the overall reaction, or you'll be given 2 steps of a reaction, the overall reaction, and asked to find the third step. Don't worry, I'm going to teach you how to do that. It's just like math. just like math. Okay? Yeah. All right. So let us just, actually, we can do it here if you would like to. We can say, oh, well, no, I haven't given enough room. What you can do is if you add up the steps, and just like in math, you say, I have a Huber on the left, I have a Huber on the right, those two can cancel out. I have 2 Hobers on the right, I have 2 Hobers on the left, so those two can cancel out. And all we're left with is 4 HBr and O2 in the reactants, and then we have 2 waters and 2 bromine in the product. So that's how you add up the steps to get a reaction, just like you would add up equations in math class, okay?
Wait, no, but in the third step, there's also 2 HBr, so shouldn't there be 5?
So there's 1, 2, 3, 4. Yeah? Is good? Okay. 1, 2, 3, 4. Reaction intermediate versus an activated complex. We've already talked about that, but just in case, reaction intermediate shows up as a product in one step and then gets used up later, whereas the activated complex, while we're at it, don't look at that, and define activated complex for your partner.
Define activated.
Activated complex. Define activated complex for your partner without reading it.
Activated complex very shortly.
Without reading it. See if you can do it without reading it.
Very shortly. It literally just breaks apart and then it comes back together. Okay. Let me confirm that. Yeah, it's fine.
Okay, I'm gonna get people to give me like properties of an activated complex and we'll kind of build a definition. Okay, it's like Build-A-Bear, but we're building a definition. All right, have you guys ever done Build-A-Bear? Do they still have that? Is that still a thing? Okay, cool. All right, Tarim, tell me one thing about an activated complex. High potential energy. It is a high potential energy. Another thing about an activated complex, Gianna. Nope, that's okay. Alex. Sorry? It happens really fast. It is short-lived. Okay, we're going to say it's short-lived. But happens really fast. That's kind of along the same lines. All right, one more thing. Not here. Zoe. Pardon me? It's an unstable arrangement of atoms. That occurs when, chat with your neighbor, make sure you could answer that question. When does it happen?
What are we doing? When atoms want to collide, when it collides, atoms collide in one of those reactions. Yeah. Those parts of it.
Okay, this one goes to Romina. It happens in the arrow. What's happening in the arrow? Yes?
Like the bones are broken, the new bones are formed.
Old bonds are breaking, new bonds are forming, and that is because what have the particles done? They have collided how?
Successfully.
Successfully. when particles collide successfully, when old bonds are breaking, and new bonds are forming. Sometimes it's nice to, if you've got a definition that have little parts to it, it's nice to kind of organize it, because then you can kind of visualize your answer a little better than if it's all in one sentence. Like if it's just like a little paragraph, it's harder. But it's like, okay, I have to say 3 things about my arrangement of atoms. I have to say it's high potential energy, short-lived, unstable. What is it? It's an arrangement of atoms. When does it happen? It happens when 2 things, particles collide successfully, and when old bonds are breaking and new bonds are forming. So sometimes that can be helpful in remembering all the aspects of a definition. Yes? Okay. Cool, cool. All right. Go. Okay. Okay, we don't need to do page 84 because we've talked about that. I don't even think we need to know this stuff, because what did I tell you about the likelihood of you ever having to write a formula for an activated complex? Almost never. But let's say we had to for step 2. You would just take the Huber and the HBr and smush them all together. So you would end up with 2 H's, 2 O's, and 2 Brs. Does it matter which order you put them in? No, it doesn't, because you have no idea. Now, what do they think maybe it looks like? What do chemists maybe think it looks like? They think maybe it looks like when you get an HBr and an O2, maybe the activated complex in step 1 looks like that. Maybe, but who knows really? Okay, we don't. Rate determining step. It is the slowest step in a reaction mechanism. It limits how fast the reaction can go. A reaction cannot go faster than the slowest step. Just can't do it. Nope. And we're going to do a little dishwashing demo. So I need 3 volunteers to come up and be my dishwashers. Excellent. Excellent, excellent. Come on up.
Oh my god. You should raise your hand too. Oh, also tired.
Okay, and we're going to turn off the projector because otherwise it's going to blind you. Okay. There we go. So you guys are just going to stand in a line like right up here. Okay, and I'm going to grab my pencil crayons. My pencil crayons are going to be my dishes. Okay, so I've got lots of them. And I'm the restaurant owner, and I got the dishes, and you're going to stand in line with them there. Okay. And what we're going to do is that James is going to be my disgruntled dishwasher. Okay? He's like, Miss Spence is a terrible boss. I hate her. I hate my job. I hate my life. It's all horrible. And I just don't care about how clean the dishes are because I'm being paid minimum wage. So you're going to wash the dishes as fast as you can, and you're going to pass it on to Romina. Not yet. You're going to pass it on to Romina. And Romina, you are going to be like the keener. Okay? Like, is that still a word? You guys don't know what a keener is, do you? No, a keener is a tryhard. Okay? Yeah, that's what it was called back in the 80s. Okay, it was called a keener. But only in Canada, apparently. It was not a thing in the States. Which is why you may not have even heard of it if you've like watched old movies or whatever. So anyway, you're the keener. You're like wanting to get ahead. You want to get a promotion. You want to be like, running a restaurant someday. So you're like, okay, And so you're going to dry the dishes really, really well. Okay, so you're going to be like, let that just dry them off and make sure they're super dry. And then you're going to pass them to Beta. And Beta, you're another disgruntled employee who's sad about everything. So you're just going to place them here and be like, "Nah," right? Not worry about that they get broken or whatever. You just throw them there and then you're done. Okay. You cannot hold more than one dish. Okay. And I'm just going to have dishes here. As soon as you are done with one dish, grab another one.
Oh, okay.
Okay? No, be slower. You're
You're supposed to be slower.
Yeah, you're supposed to be very, very slow. Okay, you have to come and get one.
What?
Hey, you're
What?
quick. You're fast.
I'm supposed to be fast, but I have to wait, you know. I'm supposed to wait, you know. Oh, okay.
Sorry. So who is limiting how fast we can go? Romina. Okay, now we're going to swap it out. We're going to swap it out and we're going to say, Beta, you are now the cleaner. Okay? You're going to go and you're going to put the dishes exactly where they should be. Okay? Which is over by the fire extinguisher in the corner.
Oh my god, why is it so far?
Okay? Do you see in the corner?
Oh, yeah.
There's a fire extinguisher. You're going to go place them over there.
Should I like be fast?
No, you're going,
slow.
you know, you don't want to break the dishes on the way. That'd be tragic.
Yeah, but if you're too slow, you could get fired anyway.
Okay, so here we go.
Wait, I'm supposed to be fast, I forgot.
And you're going to be faster than me.
At this point, can I just like walk over to myself?
Exactly, right? Nobody can go faster than the slowest step. Thank you, Beta. We're not going to make you do it anymore. And now, just for completion's sake, we're going to have our two disgruntled employees, and you, James, are going to be the perfectionist of dishwashers. Okay? Or would you like me to be the perfectionist of dishwashers and you can pass the dishes to me?
No, I'll just be.
You'll be the perfectionist. You have to really be a perfectionist. You have to examine the dishes.
Okay.
Make sure that, you know, oh, I missed a spot there, right? Okay, this is your job. All right, off we go. Washing it. Remember? Okay, you don't wash dishes like this. Have your mother never taught you to wash dishes, or your father?
I work in a restaurant.
You work in a restaurant. Okay, pretend you're washing the dishes. And you can just put it down. There we go. Can we go any faster than James? No, so it doesn't matter whether the slow step is the first step, the second step, or the third step. Whichever step it is, it limits how fast we can go. Thank you guys very much. You each get a bonus mark on your next one.
Whoa.
Yay. Yay.
Thank you to our volunteers.
We actually
Yes.
Yes.
I just got to write it down so don't forget it.
write it down. We get bonus marks. I can get 110% on my quiz now.
Okay.
Or have a chance of getting water. That's not possible. Like freaking quiz that lets me drink Mondays.
Oh, I forgot to tell you guys. So the way I assess is I use old government exams, right? So I know how hard the exams are. Okay, like I can when I used them, they had statistics for every question. It was like 73% of students got this question right, or 85% of students got this question right. So I have like 9 versions of every test, and they all work out to, an average of, whatever the average was for the province for all the years of government exams. Okay. So for example, I think, acid base part 2, the average for the entire province over all the 20 years that they ran the exams was 60%.
There's obviously people that just.
So, yeah, there were people who like couldn't do it, right? And I've never had classes get an average that low. Do you know what I mean? But I assess like that. Now, back when we had provincial exams and I would send my students to write the exam, and then I would also have my school mark that would contribute to their overall grade. My grade and the provincial exam mark were usually right bang on target. Okay, so on average, my students got approximately the same mark in school as they did on their government exam, which meant that I was doing a pretty good job of assessing people and figuring out what they knew. Yes? However, the rest of the province, their school marks were usually inflated by about 3%, which meant that even though I was doing an awesome job of assessing, thank you very much, they were doing a lousier job and they were giving their students 3 extra percent. So I decided that I would keep assessing the same way as I always did, but I would give my students 3 extra percent. So whatever you get at the end of term, I will take that mark. I have to do it manually. I cannot do it on the computer, won't do it for me. The program doesn't work that way. I will take whatever you get and add 3%. Yes? Sometimes. But what it means is that I get to assess the way I like to assess. Yes? So when it comes to sitting around and arguing with me over a half a mark on a question where you've already come and asked me about it and I've explained it to you, and then you're like, but I think, then at that point, if you're, I think, I can say, all right, for you, there will be no 3%. You can, but I think all you want. Do you know what I mean? Like, I don't want to have arguments over how I mark things. Yes? I don't mind explaining how I mark things. If you think that I did something wrong, please come and ask me when I've marked something. Please do. Often I will, change my mind or whatever. I'll be like, oh, I did not read that properly, or, oh, I thought you meant something else, or whatever. But a lot of the time, I also don't, right? And I think I mark fairly, and I give you that 3%, and that 3% sort of takes care of anything you might think is a little unfair or whatever, or I'm being too picky or whatnot. Yes? Okay, are we good with that? Cool, all right. So the slowest step determines the rate because we cannot go any faster than the rate determining step. And if you want another visual for that, other than the dishwashing demo, you can think, if I had funnels and I was not allowed to overflow the funnels, I could not pour the liquid any faster than the smallest funnel would allow. Does that make sense? Okay. So here we have, so any reaction, actually, I'm just going to pop back to this one for a moment because it is labeled slow, fast, fast. Does it matter how much faster the 2 fast steps are? Does it matter if one is faster than the other? No. So we just label one of the steps slow and the others are just fast. Okay? So anytime you have a slow step already, none of the other steps can be slow. So if we have this 3-step mechanism here, step 3 has to be fast or slow? Step 3 has to be fast because we already have a slow step. Only one slow step. Could you please circle any reaction intermediates?
Chlorine. Chlorine. Like it was chlorine. That's one.
CCl3 is a reaction intermediate. And sometimes I like to, give them different shapes when I circle them. So maybe this one I'll be like, oh, look, I'll give that one a square. And it gets used up. One of them gets used up in step 2. One of them gets used up in step 3. Do we have any more? Or is that it? No, we don't. So let's add up the steps to find the overall reaction. So basically all you do is you say, I'm just going to cancel these all out and I'm going to add it up. If you guys could please do that. And one thing you'll notice here is that even though this is only a 2-particle collision, we still have a mechanism here. And that's okay. You don't have to have many particles. It's just that that's often why we end up with a mechanism. One thing that I found my AP students thought last semester, they thought having a many-step reaction mechanism made a reaction slow. It does not. Okay? Having a many-step reaction mechanism does not mean that a reaction is slow. It could be slow, it could be fast, but it doesn't depend on whether there's a mechanism or not. Basically, it still just depends on the activation energy, okay? Right, the products of the overall reaction, we did that. Write the formula of the activated complex for step 2. What would the formula for the activated complex of step 2 be? It would be CHCl4 with a star. Just take your 2 things in step 2, which is 1 carbon, 1 hydrogen, and 4 chlorines. 1 carbon, 1 hydrogen, and 4 chlorines, and then put a star on it so it's an activated complex. But like I said, chances of you having to do that are very low. All right, let's see what else we've got here. There's our solution. We are going to do find the missing step. Okay, so find the missing step. So this following reaction occurs in a 3-step mechanism, and we are given step 1, we're given step 2, and we do not know step 3. What that means is that this reaction here, this is our overall reaction. And usually when I add things up, I like my total to be at the bottom. But you will often be given the total at the top because, like, here's the reaction, here's some steps, what do you get? So one of the first things you do when you're finding the missing step is you put your overall reaction at the bottom. And I like to line up my arrows so that my reactants are obviously on one side and my products are obviously on another side. So my step 3 is going to have my arrow there. There's my overall reaction. And I have 2A 4 plus B plus. I'm just copying the reaction that's in yellow, okay? 2A 3 plus B 3 plus. And now I like to go through and I circle things that I have in the reactants that are also, that are in my steps that I also have in my overall reaction. So I say, I have 2 A4 pluses and I have 2 A4 pluses. So those are all taken care of. I don't need to do anything with those. I want them there. Yes? Is there anything else that I have in my products or my reactants that is also in the overall reaction? I've got A3 plus. So I've got this here, I got this here, and I've got it here. Whoa, what happened there? So we have some stuff that's missing. So let's go and put in the missing things first. Okay, so we need some B pluses. So we need to have a B plus. And we need to have a B 3 plus. I guess I could have done some other circle for that or whatever. Maybe I'll make those circles. Am I done? No. What do I have to do? I have to make sure everything else cancels out. Is there anything that can cancel out already? Yes. What can cancel out already? A's can't cancel out because they have different charges. Charges have to match for them to cancel with each other. But what do I have that matches in every single way? I've got C3 plus. Okay, so I've got a C3 plus and I've got a C3 plus. So those can cancel out. What else needs to cancel out? C2 and C4. So where will we put the C2 so that it cancels out? I'm going to put it on the right side because then it will cancel out. C2 plus. And then I'm going to say, is there anything else that needs to cancel out? I have a C4 plus. So I'm going to put a C4 plus here. I need to put some pluses in between my reactants and my products. And now we have a step 3. And we're complete because this will cancel with this. This will cancel with this. And all we're left with is 2A4 pluses, 2A3 pluses, a B plus, and a B3 plus, which is exactly what we wanted in our products. So the basic steps are to look for everything that is in the overall reaction and circle them. Circle everything in the steps that is in the overall reaction. And then you just leave those alone. Don't touch those. Second thing you do is you cancel out anything in the steps that can cancel. And then the third thing you're going to do is you're going to put any reactants or products you need into the missing step. It doesn't actually matter. The order of step 2 and 3 doesn't matter. Put any missing reactants or products into the missing step. And then for add things that need canceling to the missing step. Is good? Okay, wonderful. I don't know that having the steps written out is as useful as just practicing the steps because, you know, there's a lot of words there and they don't always seem to like, I don't know, make sense. But practicing these things is really good. So let us see if we have some practice here. No, not yet. So you could do Hebden, page 28, number 46, 49, and 50 to 52. Actually, you could do everything on page 88. And we have what, 12 minutes left? Do you want some time to work on that? Okay, cool.
Since we're working on, can you go back to the steps?
Yes. There we go.
Okay, just look at that.
Yeah. No, what I said is that the 3 steps are the mechanism. Yeah.
Mechanism is like a multiple step until
Yes.
we get the final reaction.
Perfect. Yes. And that should be an arrow, not a equal sign.
Oh, right.
Yeah. Perfect. Yeah. And if you want to work on a Hebden right now, there are Hebdens over on the shelf. Just over here.
So if I like borrow that.
Yeah, you can just borrow a Hebden for right now.
Oh no, like I like get a.
Oh, you want to borrow one? I'll drop it over for that. Wait. You'll see a drop in very high.
I just know that, I remember like, I remember seeing people with this with kids.
The other one. Yeah, you want to go further left. There you go. Yeah, so solid to the slope. Right now. Anything that. Yeah.
I have book cards.
Oh, you got a grade 11 one. You want a grade 12 one.
You did say one. I have grade one.
Go to the far left. That's perfect.
Oh, sorry, thank you. Might as well get a worship condition. So when it's already in back. That's the strap. Oh my god, I gotta put my backpack. Oh my god. What happened?
And if you want to know the Hebden sections for the quiz, it's 1.3.
Just have them go like one higher.
No, it's just, I don't organize my stuff the way Hebden did. So, because my brain works differently.
We just look names.
310. Hebden Chemistry 12. Yeah. Perfect. Thank you. Hi.
Explain this part again. I was listening, but like now I get confused.
Don't worry. It's all good. So if you have only two particles, they can randomly collide and eventually they'll collide correctly. But it's going to take a while. If you have three particles that all are moving in all different directions and they all need to collide exactly perfectly,
That's harder.
that's very hard. The
That's
probability becomes very small. That's why we break it into a series of steps, each of which only has two particles in it, or maybe one particle.
Oh, that's why we're showing every step.
Yeah, exactly.
So why does that make the activation energy like smaller?
It doesn't necessarily, it usually does. Just,
Do I just have to memorize that?
oh,
Here.
no, this means the probability is extremely small. Yes, the
Okay.
probability is
Okay,
extremely
that
small.
makes
There we go. Yeah,
What room is this?
310.
Thank you.
Perfect, thank you. I know, that's blinding. I'll turn it off now.
Quiz will be the most annoying quiz to study for, actually. There's so much things to memorize. Yeah. Just if it's it would be that. It's not even so many equations, it's memorize. It's the key. Huh? I don't like this. Oh, memorize things. Why is there a lesson plan here? I am not teaching that lesson and I'll never teach that lesson. I'll do this. Support. Can my print not open now? Is it too heavy? Oh my gosh, I still got memory.
But it was nice for the cameras that we saw how clean it was today. It is.
I guess, you know what? So, especially when you know, and it's very fast. Yeah, you know, like it's not fast because like you know,
Well, and that's why I usually have it.
yeah, because like you know, I just like right now, like for like 1 month, I didn't want it. Before I had
Yeah.
for example. That's
Just a reminder that Douglas College representative is here today at lunch in room 200. Douglas College, today at lunch in room 200.
Bye.